Okay, so we've talked about covalent bonding, ionic bonding, metallic bonding. And for covalent compounds, we have to call them molecules, and those molecules get Lewis structures. So basically, Lewis structures are ones that show how the atoms are covalently bonded together. So there are instructions to how we draw these Lewis structures. So let's start with, the first thing is you have to know the number of valence electrons, so you have to count it all up. Then you do the skeletal structure, which is you put the lowest electronegativity element, usually in the central atom. And hydrogen never can be central because hydrogen is an exception to the octet rule. Then we put lone pairs. These are the pairs after we bond them. We place the lone pairs. These are the ones that are not used in bonding. We make sure that things that need to satisfy the octet do. In some cases, we need to think about multiple bonding, and that's usually just these elements. You don't really see multiple bonding with any other ones except carbon, nitrogen, oxygen, phosphorus, and sometimes sulfur as well. Fluorine and chlorine will never multiple bond. And if there is an exception to the octet rule, there are a few that can go above the octet. That's known as expanded octet. And then there are ones that just are exceptions, like boron is stable with 6 electrons. Hydrogen is stable with 2 electrons. So in order to draw a Lewis structure, first we need to look at the compound, right? So let's look at a compound such as carbon with 4 hydrogens. First thing, as it says here, count the total number of valence electrons. Well, carbon is in group 14, so I know it has 4. Hydrogen, each hydrogen has 1, and then there are 4 of them, so that's another 4. I have a total of 8 valence electrons that I need to worry about. Then it says to write the skeletal structure, arrangement of atoms. So you have, what is in the middle? Well, between carbon and hydrogen, we just said hydrogen is really never in the middle because it's stable with 2 electrons, so you can't really bond more than that. So we're going to put carbon in the middle. And then since carbon is a group 14 element, think about how many bonds it wants to make. It wants to make 4 bonds. So we're going to go ahead and draw. So each of these lines, each line represents 2 electrons. Those 2 electrons come from, one of them comes from one atom, so hydrogen puts in an electron here, and carbon puts in an electron here. Again, same thing, hydrogen, carbon puts its electron, hydrogen, carbon, hydrogen, carbon. And so instead of drawing out the dots, we just draw out lines for those bonds. So the line represents a bond. Now, since we had 8 electrons, 1, 2, 3, 4 bonds, each of them 2, 4 times 2, you have 8 electrons, and each of the octets, or the duet, in the case of the hydrogen, it's stable with just 2 electrons, so it has one of its own, it shares one with the carbon. So let's do a few example problems. Okay, here we go. So CH4 we just did, we'll put it here as well. Now let's look at NH3. So first thing you want to do is count out the number of valence electrons. Nitrogen is a group 15 element, and each hydrogen has 3, so there's a total of 8 that we need to account for. Each hydrogen is 1, sorry, there are 3 of them. So we're going to put nitrogen in the middle since hydrogen doesn't belong in the middle. Okay, so now this is 2, 4, 6 electrons. So where's the other 2 since we have to count up all 8? So the other 2 is on the nitrogen. Why on the nitrogen? Well, because the hydrogen is already done here, and nitrogen had 5 valence. It shared 3 of its valence, so it put 1 here, 1 here, 1 here. So it still has a pair left over. Okay, let's look at water. Water has 2 hydrogens and an oxygen, total of 8 valence. So this oxygen goes in the middle, and you've probably seen water being drawn bent like this. We'll talk about structures later, but you can draw it straight or bent for now. So now what has happened? Oxygen used 1 valence there and 1 valence there, right? But there's 8 total, so 2, 4, so there's still 4 valence electrons we have to account for, which go on the oxygen, okay? Then let's look at the next one, silicon tetrafluoride. So silicon tetrafluoride. So silicon is a group 14 element, so 4 valence. Plus, each fluorine has 7. How do I know that? Because fluorine is a halogen in group 17, therefore 7 valence. 7 times 4 gives me 28. So now I have to account for 32 electrons. So, looking at this compound, can you tell which one should go in the middle? So between silicon and fluorine, remember the less electronegative one goes in the middle, usually. So here's silicon. Now we have 4 fluorines. So we're going to put them all here. Now that gives me 8 electrons, right? 2, 4, 6, 8 from the 4 bonds. So I still have 24 that I need to account for. And if you look at the number of valence electrons, remember fluorine had 7. So each fluorine atom is going to have 3 lone pairs. So we call each of this a lone pair. A lone pair is a pair of valence electrons that are not used in bonding. However, they're still there, so we have to account for them. All right, next one is nitrogen with 3 chlorine ions. 3 chlorine atoms. So you have nitrogen, group 15, 5 valence. Chlorine is group 17, 7 valence, 21 plus 5, 26 valence electrons. So put nitrogen in the middle. You have 1, 2, 3 chlorines. Okay, that's 6 electrons. Now I have 20 more electrons to account for. I know that chlorine still gets 3 more pairs of lone. And that gives me 18 electrons. And there's 1 more pair left on the nitrogen. So just count it up and then you'll see where it's supposed to go. Now, we'll hold on to the polyatomic ions for now and switch on to multiple bonding. Let's look at this compound, H2CO. So 2 valence electrons from the hydrogens, 4 from the carbon, and 6, so 6, 4. So you have 12 to account for. Now, how would we draw this? So if carbon is still the central atom, and we are going to bond each hydrogen to that carbon, okay, great. But now carbon is still not an octet. The only thing right now that's satisfied are the hydrogens. We still have an oxygen to account for, so let's put the oxygen here first. Okay, now what happens in this case is carbon has 4 valence, right? So there's still 1 more. There was 12 total, so 2, 4, 6. I've only accounted for 6. And so I still have 6 more. Now, if I put a lone pair on the carbon and then 2 lone pairs on the oxygen, we have a problem. What is the problem we're faced with? Is that oxygen won't be octet. So oxygen won't reach its 8. That's a problem, right? And carbon will end up with a lone pair, which is really not what carbon wants. So what if we did double bond, right? So 2, 4, 6, 8, and then oxygen still gets its 2 lone pairs. And that satisfies carbon's octet, it satisfies oxygen's octet, and hydrogens are already stable. All right, the next one. You have HCN. And so what are we going to do with this one? Hydrogen, carbon, nitrogen. So think about it. Carbon really wants to make 4 bonds somehow. Nitrogen likes to make 3 bonds, and hydrogen is happy with 1. So it's going to look like this, where you're triple bonded to nitrogen. Count up the valence and see that that is going to make sense. I'm not going to do monoxide because you don't need to know that one. Let's look at carbon dioxide. So what I want you to do is I want you to go ahead and pause right now. Count up the valence electrons, figure out what carbon dioxide would look like where every single element is satisfied with its octet and carbon is your middle. So take a minute to do that on your own and then come back for me to go over it. Okay, so hopefully you paused and you went in and did this, and I'm hoping that you ended up with this, where carbon is double bonded to each of the oxygens. So you had 12 and 16 electrons, right? 2, 4, 6, 8, 2, 4, 6, 8. So 8 valence, 8 shared and used in bonding, 8 lone pairs, 8 electrons, 4 lone pairs on the oxygens, and that satisfies all the octets that they need. Okay. Now, with polyatomic ions do some funny things with the way that they're bonded and why they have a charge. So polyatomic ions are a group of covalently bonded ions, but for some reason, well, there's a reason, but for right now, for some reason, there's an overall charge. So these charges that you see here, that charge belongs to the entire compound. However, there are no ionic bonding here. It's all covalently bonded. So in these cases, there's something called expanded octet sometimes, where it has more than 8 electrons surrounding it. As long as you count for all the electrons, then it'll make sense. But I'm gonna leave polyatomic ions alone for the time being and do some more practice of just the regular Lewis structures. Okay, let's look at something like pH3, and then we'll look at C2H4, and we'll look at just very simple one. All right, so let's look at pH3. Phosphorus, group 15, 5 valence. Each hydrogen has its 1, so there's 3. You have 8 that you need to account for. You put phosphorus in the middle, because remember, hydrogens can't belong in the middle. And then a lone pair on the phosphorus. Now, there's a shape and a geometry to this, right? When you look at the 3D version of this molecule, there are certain angles here that we're going to talk about, and there's a name to this geometry that we're going to get to. Let's look at C2H4. So think about 2 carbons. And since you have only 4 hydrogens, and that's what that looks like. What if you just had something as simple as diatomic molecule of fluorine? Fluorine really just wants to make 1 bond, and then it's going to have 6 electrons that are not bonded in anything. Now, let's talk about geometry. When the molecule comes together, the bonds bend at a specific angle to minimize repulsive forces. Okay. VSEPR stands for valence, shell, electron, pair, repulsion. What that means is when you draw a water molecule, you can't draw it this way, even though it's fine if you do. But the reason we always draw the water molecule this way is because the lone pairs of electrons and the bonded pair here, there are repulsive forces, right? Why are they repulsive forces? Well, they're both negatively charged, so it's going to repel. And so what it does is when it repels, it bends. But how much can it bend? It bends so that this is also far apart from each other, because you don't want these bonds to come close and start pushing each other. So you have these lone pairs of electrons, you have these bonds, so they're structured in a way that is going to minimize repulsive forces. So there's an angle about 109 degrees between each of these. The lone pairs have more repulsion than the bonded pairs, and that should make sense because lone pairs are taking up more space and they're not neatly tied into a bond. All right, so before we talk about VSEPR, we'll look at some more Lewis structures. So let's think about, this is an exception to the octet. Okay, so boron is an exception. It's a atom that's stable with 6 instead of 8. Okay, so boron has 3 valence electrons. It goes and sits in the middle. You have iodines around it. And each of the iodines have 3 lone pairs surrounding them. And boron is stable this way. Now, along with that, these bonds are at 120 angle from each other, and that minimizes the repulsive forces. And the geometry for this is called trigonal planar. Okay. A molecule where nitrogen and 3 iodines are bonded to it. We're going to put nitrogen in the middle. This is not an exception to the octet. Now, this one has a lone pair of electrons. The lone pairs of electrons push at these angles a little more. Okay, sorry. One note just kicked me out. Give me a second. Okay, sorry about that. It kicked me out. So, the lone pair on the nitrogen for this compound, this one right here, pushes at these bonds a little more. So then these have a certain push to them. And so what ends up happening is it's about 107 to 109 degrees. And we call this trigonal, but we call it pyramidal. Pyramidal. Sorry, that's a D. Okay, so that shape is different than the trigonal planar. And what's the difference? Each of them have 3 things bonded to them. However, this one has a lone pair, and the lone pair makes a huge difference on the angle and the shape. Okay. All right. Then we have a central atom with 4 atoms bonded to it. So let's look at something like CH4. This is called tetrahedral. Tetrahedral is a central atom with no lone pairs, but there are 4 bonds, and these angles are 109.5. Then we have one that's linear, and linear is 180. Okay, and I'm going to give you a list of all the types of VS-EPR geometry. It's going to be on the calendar that's on my JAG, and I have a practice worksheet for you to do today. So go ahead and click on that, and you'll also have hard copies that you can get from the sub. You're going to work on both Lewis structures and VS-EPR geometry with the Lewis structures. And you'll work on that worksheet for the rest of the period. What you don't finish is homework, and then we'll go over it together and we'll move on to the next thing. All right, have a wonderful day.